Hello and welcome back to the second unit of the DeepPumas onboarding material. And in this talk slash presentation, I'll be talking about machine learning and neural networks. So if you're familiar with these concepts or some concepts from machine learning and neural networks, some of these slides might be a bit old or a bit repetitive. But also towards the end, we talk a bit more about the idea of generative models, conditional generative models, and where these kinds of classes of machine learning models fit in with nonlinear mixed effects modeling. And that can still be quite insightful, even if you're not aware, or even if you are aware of machine learning concepts and neural networks. So please bear with me and feel free to skip to the parts that are not familiar to you. If some of this material is already familiar. So let's get started. So maybe a little bit of background first in terms of the context and the evolution in the recent history of machine learning. So at least in our field, or some of the papers in our field in pharmacometrics or PKPD have been highlighted here, but some other papers also that have been sort of milestones or iconic papers that made a big shift in the field of machine learning. And so some of the computer vision advances happened back then in 1998 when the LUNET paper came out and the architecture. Before that, the time series modeling and different architectures for time series modeling have been proposed. And then even before that, actually, interestingly, close to perhaps 1996 or around 1996, Joga, Goburu, and Chen actually had used neural networks for PKPD, which is sort of the main application domain that we work with often. And so you'll see that it is a field that has been developing actually even from way before that. But these are some of the iconic moments that happened even before the year 2000. But then you'll find that in machine learning in general, there are sort of theoretical advances or like new methods, new architectures come out. But at the same time, there is new software that comes out, often supported by some big corporations. And this software then helps speed up and accelerate the development of more theory and more architectures. And so one of the first sort of advances on the software front that was quite transformational was this software called Theano. And Theano was basically a tensor library, like similar to PyTorch and TensorFlow more recently. But it was one of the first sort of libraries that enabled easily building different architectures of neural networks and doing backpropagation or automatic differentiation on that, and then training it quite easily. And so it was one of the more transformational moments of the history of the software in this field. And you'll see that, again, software inspires more innovation, enables and empowers scientists who are not necessarily software specialists to do more kind of research and application research. We're applying neural networks, applying machine learning to different fields. And then we all know that at some point PyTorch and TensorFlow, these are some of the most iconic also software tools that are still used till today for developing neural networks. They came out roughly around 2016. And again, they sort of triggered a wave of innovation that came with them. Many interesting papers came at that time, some in medical or in general, like health and healthcare and medicine have been two of the biggest applications of machine learning historically, but also things like architectural innovations like the neural differential equation or the neural ODE came around 2018 as well. And then, again, more innovations kept coming, inspired by essentially software. Now, Pumas is a pharmaceutical modeling and simulation software. It may seem like it has nothing to do with machine learning, but as we'll see by the end of this talk, actually, Pumas and the class of models that Pumas allows you to work with, which is nonlinear mixed effects modeling, is indeed actually a type of machine learning. If you just throw in, depending on how you define your architecture, you can actually call it a machine learning model, and actually a lot of machine learning models can be represented and even trained directly in Pumas. And then by extension in DeepPumas, where we actually enable you to use also neural networks more freely and easily in there, and then mix it with more mechanistic modeling. And so that's perhaps a very brief history. It may not look like a very long history, but actually the theory and the methods of machine learning and neural networks, they go even way back before that. It's just that back then the software and the hardware were not quite advanced yet, and so only very few people could actually do this kind of research, and you couldn't easily scale it to very large networks and very large data sets. But with modern hardware and with modern software, that allows you to more easily and makes it more accessible to train and define these large neural networks. Basically, machine learning now is more accessible than ever, and we're able to use it for so many applications, and perhaps our main applications of interest in pharmacometrics and healthcare. There is really no shortage of applications. There's only shortage of people who are able to apply these tools to solve some difficult problems. So that's a little bit about maybe the history. If we can take a specific study that was perhaps of interest that came in 2018, rather 2016, I think. This is a study that basically was predicting toxicity, or used deep learning to try and predict toxicity. And you'll see that they benchmarked a few different models, and basically they found that some of the deep learning approaches were able to predict the toxicity at a much higher accuracy than the rest of the methods. And so really deep learning has been quite impactful in many different fields, not just in pharmacometrics, but we really see that it does have a lot of potential in our field in pharmacometrics. And you can perhaps see more details in this paper here. Now, another area of application where machine learning and deep learning in particular can actually be quite useful is in working with images. So if you have image data or high-dimensional data in general that might be difficult to reason about, I mean, what every pixel is doing in an image and what it means, usually deep learning methods and certain architectures of deep learning models are able to actually extract certain patterns and understand certain patterns in images, and then use them to perhaps predict something. In this case, maybe we are trying to predict what kind of lesion, or how big the lesion is, or any kind of characteristic. Like it could be even in dermatology, for example, predicting what kind of disease. And so you could use this here to essentially classify. So this was an application that was used to classify what kind of lesion this is. And you can see that they compared this CNN, which stands for convolutional neural network. It's a type of a neural network that can process image data and basically make a prediction or do a bunch of other things, depending on how you tailor the CNN. In this case, it was a prediction exercise, and you'll see that actually the CNN was able to achieve a comparable performance to some actual dermatologists who had some proper training to be able to do their jobs, right? And so the CNN is essentially able to match an expert in this particular application. And so deep learning methods, again, have developed or have been developing for a long time now, especially in the computer vision area. And so right now, if you have image data, extracting information from that and using it to inform certain predictive models or make certain predictions about a clinical endpoint, for example, that is very much doable, and people have been trying to do that for a while. And we do believe that DeepPumas makes it even easier to try and combine this kind of rich data with perhaps more mechanistic models and mechanistic knowledge that you may already have about your disease or the drug or the patient and the way disease progresses. So maybe now that we've seen some applications of machine learning and deep learning, it's probably a good idea to take a step back and sort of define some of the key terminology in machine learning. And so these are common terminology that people use when talking about machine learning. They're somewhat loose terminology in the sense that you can find some algorithms that don't fit neatly in any one of them, but they're nevertheless important part of sort of the development of terminology and jargon around this field, and so people do use these terms quite often. And so something like supervised machine learning, the idea of supervision basically means that somebody has given you an input, for example, some image, and a label or an output, for example, a class of that image, if it's a cat or a dog, or if it's a specific disease or another disease, like skin disease. And so this idea of giving you the input and then the output is often called supervision. And it's called supervision because I'm giving you what the output is, and then I'm asking you to, for example, predict a certain output if it's continuous, or to do some classification if it's a discrete output, to tell me if is this image, for example, that of a cat or that of a dog, or trying to predict maybe the tumor response over time, right? So I have the tumor response, I have the time, and I'm trying to predict tumor as a function of time, for example. And so almost any kind of regression task, or pretty much all regression tasks, fall under this prediction. If you're familiar with the term regression or linear regression, it typically falls under this supervised machine learning classification or category, essentially, of machine learning. Then there is something called unsupervised machine learning, which is generally considered more difficult than supervised machine learning. And there we don't have sort of a distinction between an input and an output, or the goal is not necessarily to predict an output from an input, but I just give you some data that's generally called unlabeled data. And then you can do one of many possible things with this unlabeled data. So I can ask you maybe to learn a generative model, right, that tries to essentially learn the distribution of that data so that you can generate some data that looks like the real data. So I give you maybe images or photos of humans, and then the goal of the generative model is to be able to generate some images or photos of people that don't exist, that look like people that do exist. And so that's an unsupervised machine learning task, because I'm just giving you the data without a specific input and output. And then we could also do things like feature extraction, where I'm just trying to extract interesting patterns in my data. So if you do something like PCA, principal component analysis, if you're familiar with that, if not, we would cover it in more details. But that's considered a form of feature extraction or unsupervised machine learning. Now, if you're doing clustering, for example, I give you some data of a bunch of patients, tumor size over time, for example, and then you would like to automatically group them together into different groups, depending on maybe the partial responders, or the full responders, or complete responders, and maybe the non-responders, right? So you might have different clusters, and you want to sort of group patients or the subjects together. The ones that look like each other should be in one group, and the ones that like look different should be in another group. And so that kind of activity is typically called clustering, or that kind of task. So each of those things are typically called tasks, or machine learning task, essentially. Whether it's learning the distribution of the data, or extracting certain features from the data, or doing some clustering or classification or prediction, these are all usually known as tasks in machine learning. And then there is something called semi-supervised machine learning, which often has components of both supervised and unsupervised machine learning. So sometimes you, for example, start with unsupervised machine learning, maybe extract some features from the data, and then use those features to make a certain prediction. Right, so I can use the image, for example. I have the image from before. I can extract features from that image with unsupervised machine learning, then use those features then as predictors in a prediction model or in a regression model, which is a supervised model. So you can sort of mix and match these different approaches here. Now, there are many other sort of types and categories of machine learning that are not covered here, but these are sort of three of the main ones that you need to be aware of. And then there's another one which is also very popular, but that's actually out of scope for this sort of training, which is reinforcement learning. Now, reinforcement learning, even though it's called learning and it's part of machine learning, it actually tries to solve a very different problem that's more of an optimization problem or a decision-making problem. So the goal here is not necessarily just to work with the data or understand the data or predict the data or learn the distribution of the data, but the goal is actually to do decision-making in an environment, so in a stochastic environment. So think of it like a game. So create an agent that can play a game that looks at the environment based on the observation, makes a decision, and then either gets a reward or a penalty, and then adjusts the policy or the way that it's playing the game in order to maximize the reward or minimize the penalty. So it's a very different paradigm of applying machine learning that actually uses a lot of supervised machine learning and unsupervised machine learning as part of it, as components of it. But it's really not in scope for this training. But I just thought it would be worth mentioning that. Good. Now there is... maybe it's worth mentioning that machine learning is different from deep learning, if you ever heard these two terminology. And so there are certain machine learning algorithms that predate the use of neural networks, or the popular use of neural networks, perhaps, because neural networks are quite old. But there are some classical machine learning algorithms that don't use neural networks. If you heard this term neural network, which we will see what it means in more details. But generally, whenever we have neural networks in a machine learning model, this is often called deep learning. If the neural network is a deep neural network, then it's often called deep learning. Now, not all machine learning algorithms use neural networks. As I said, there are some algorithms that predate the popular use of neural networks in machine learning. And also, even though many machine learning algorithms use probabilistic models, which we will see a lot of in this training, not all machine learning algorithms actually use probabilistic models. So many do, but not all of them. And probabilistic models are really generally at the heart of many different algorithms in machine learning, despite, again, not all of them actually using those kinds of models. Now, probabilistic machine learning is a term that's often used to refer to machine learning algorithms that use probabilistic models, and these generally borrow a lot of concepts from computational Bayesian statistics. If you've ever studied or taken some Bayesian stats or Bayesian statistics, especially computational Bayesian statistics, you will see that there are many concepts basically in probabilistic machine learning that are just borrowed and sometimes renamed from their sort of more statistical predecessors. And so there are sort of many algorithms that have been rebranded and renamed despite being much older statistical algorithms. Things like linear regression, for example, would be considered a supervised machine learning algorithm, despite, again, having much older history in statistics. But as I said before, not all machine learning algorithms use probabilistic models. So generally, machine learning algorithms are just designed to tackle a specific problem or solve or perform a specific task. And so if it's able to do a task without a probabilistic model, and it's able to train and learn from the data and get better with more data, then it is a machine learning algorithm despite not using any probabilistic modeling. And so for clustering, for example, or classification or prediction, there's a certain approach or algorithm called the k-nearest neighbor algorithm, which literally just looks at the k nearest points. If I have a new point, it looks at which maybe 10 points or 5 points are most similar to this point, and then based on their prediction, I can take the average or the most sort of the mode. If it's a discrete classification problem, take the most sort of repeating class among these 5 points, and that's my prediction, right? And so you could, or that's my classification output. So you could develop algorithms that don't use any probabilistic modeling, yet they still perform the task that they set out to perform, which is a machine learning task, and they learn from the data, and they can be trained on data, and so on, yet they don't actually use explicitly any probabilistic modeling. Another would be decision trees that, again, just based on some conditions and criteria, if x is more than 1, if x1 is more than 1, if x2 is less than 3, for example, based on these conditions, it might predict one output or one class or the other. And so these decision trees are also typically not based on any probabilistic modeling, and they're just rule-based sort of models, yet they can still perform pretty well, and you can train them such that they again learn from the data, and they're able to actually perform better the more data they see, and they can overfit and all that stuff. And so just because it's not a probabilistic model doesn't necessarily mean it's an underpowered model. It can still be very powerful despite not being probabilistic. In fact, there are many clustering algorithms as well, like hierarchical clustering and DB-scan and many other methods that do not actually use probabilistic modeling. Now, historically, there's a whole field called data mining, So the term data mining is sort of an older term that people don't use much anymore, but it used to be mostly dominated, this whole field, or people working in data mining, that field used to be dominated with methods that don't really use probabilistic modeling. If you ask a data mining person, they'll tell you data mining is more than just machine learning, and it encompasses machine learning, and is more than just probabilistic machine learning. But the community of data mining researchers typically basically created many of these algorithms that were not really probabilistic in nature. But nowadays people just use the term machine learning to refer to any kind of task that involves learning from data. So machine learning is not all new. This is, again, another very important sort of disclaimer that machine learning often and very often actually builds on and reinvents many other fields. So you take a very simple algorithm from statistics, like factor analysis, for example, in statistics. It has another name in machine learning. Optimization, different optimization algorithms have been sort of tweaked and tuned a little bit to be used in machine learning. A lot of techniques from image and signal processing have also been used and adapted for machine learning. Obviously, software engineering has been quite important in the history and the evolution of machine learning as a field, historically, because like the getting these very large and complicated models to handle large data sets is not easy for perhaps a domain expert to do. And so the easier the software is, and the easier it is to use and to deploy and to train on large data and so on, the more accessible and the more people can actually innovate with these tools. And so machine learning has been sort of borrowing concepts and building and connecting together concepts from all these different fields. And again, it is basically centered around, it's mostly a task-driven sort of research area where the machine learning researcher will define a specific task or pick a specific task and then try to do it in the best way possible by designing different algorithms and different architectures and different models and so on. And so as part of solving that specific task, they could make use of different statistical concepts or statistical methods, different optimization methods, and so on. Now, some related terms to machine learning would be data mining. Data mining is again all about extracting certain non-obvious patterns from the data, which is a very general definition that you could think applies to also machine learning. And they're again, despite some maybe historical debates, they're more or less used as synonyms, or they refer to different sort of like they're basically describing the same concepts, just using slightly different words and different emphasis. And data mining historically used to focus more on the data part and storing the data and how to store it in databases. And there was it's almost like an extension of database management systems and extracting information from the data clusters and so on, or the data centers. And so they have slightly different focuses, but they are very much related fields. And if you open a data mining book, you'll find that more than half of it is basically using or covering machine learning algorithms. Data science is another broad term that people use to describe the science of working with data, which is again a very broad definition that pretty much encompasses anything that has to do with data. So you could say that it does encompass machine learning as well, or it might be synonymous. A lot of data scientists are essentially doing machine learning, although some people would use this term to refer to maybe more working with data and pre-processing the data and cleaning the data and storing it in like databases and so on. So depending on who you talk to, different data scientists might be doing different things. So it is a very broad term that I don't think is particularly useful per se, without any more details as to what the person is actually doing if they're just a data scientist. And then artificial intelligence is probably the least useful term of all, because it covers so many topics and so many things, including machine learning, including like a lot of optimization methods, and many other basically topics in computer science have been rebranded as artificial intelligence one way or another. Knowledge representation and a lot of different fields basically fall under AI or artificial intelligence, and so that term you'll find being used a lot for marketing and so on, but often until you actually see what the person again is working on or talking about. It's really hard to know just by saying, oh, this person is doing AI. Just like that's not enough to actually know what they're doing. They could be doing literally one of 100 different things. So very general terms like this are typically just used as marketing buzzwords, but not really. They're not necessarily very technically useful definitions or terms. Good. So I think the controversial part is more or less finished. So let's move on to perhaps the more technical parts. And so we'll be focused on for the rest of this presentation on probabilistic supervised machine learning. So it is a machine learning algorithm because we learn from data. Machine is learning from data to try and perform a specific task. It's a supervised machine learning algorithm because there is an input, a very specifically well-defined input, and a very specifically well-defined output. And the goal is to predict the output from the input. Now the output can be continuous or discrete. We'll come to that. And it's probabilistic because we use probabilistic models as the main workhorse of this whole approach here. Good. So the scope of supervised machine learning is that we generally have this data that's labeled data, as we called it before. So labeled data means that we have an X and a Y. The Y is often called the label of the data for some reason. And we could have endpoints. So n here is the number of data points that we have. So again, you can think of this as any sort of tabular data that we have. So we could have some baseline covariates here. We could have whether the patient is a responder or non-responder. So there could be like a 0-1 sort of output here. We could have the exposure as the X, and then we can have the response as the Y. All right, so we can develop an exposure response model. So exposure response models are generally supervised models, basically. Now, they may use machine learning, but they don't have to. If you use a simple linear regression model, that can be considered a supervised machine learning model. And so we often have, again, some input X, some output Y, and we want to predict Y as a function of X. Now, this could, again, be prediction if the outcome is continuous, or it could be classification if the outcome is typically basically nominal discrete. Now, if the outcome is ordinal data, then I guess it could be called prediction, technically, but you're just predicting an ordinal number that basically, like order matters. The difference between ordinal data and nominal data is that with ordinal data, 2 is bigger than 1, 3 is bigger than 2, 4 is bigger than 3. So you could be predicting maybe the shelf number in a library or something like that, and where each book would be going in that library. And so there, the shelf number actually, there's an order. It refers to a specific order. Therefore, it's called ordinal data. And with nominal data, there's no order. It's like a dog or a cat. A dog is not greater than the cat or vice versa. And so it's just two different classes, essentially, or 3 or 4 different classes that we might be classifying. And so prediction could also technically be used for ordinal data. But generally the focus here is to predict Y given X, right, or conditional on X. And so we're not interested in actually modeling X itself. X is not the main target. It's just that if I give you X, tell me what Y should be for that specific X. So that's sort of the main question that a supervised machine learning model is trying to answer. Now you can call it a conditional model as well because it's Y conditioned on X or for a given X. Often it's also called a discriminative model. And that's sort of to discriminate between this kind of models and another class of models called generative models. And so in discriminative models, we're just trying to essentially discriminate between 2 data points, which one has a value of, let's say, Y equals 0 versus Y equals 1, whereas in a generative model, usually we're trying to generate the data or learn the distribution of the data. So you'll find it called a conditional model, you'll find it called a discriminative model, or just a supervised machine learning or prediction or classification or regression model. So there's many sort of names for this class of models here. So now let's take some examples of a few supervised machine learning models. So a prediction model or probabilistic supervised machine learning models. So this here is an example where we're trying to predict essentially Y from an input X, and Y is unconstrained. Unconstrained meaning that it can be positive, it can be negative, it can be 0. There's no specific constraint on it being, for example, non-negative or between 0 and 1 or something like that. And the reason that this brings us to a very important concept, which is when you're trying to build a predictive model, you need to make sure that the predictions you make fall in the interval or in the domain of the actual variable you're trying to predict. So if you're trying to predict a variable that's only positive, your prediction should never be negative. If you're trying to predict a value that's between 0 and 1, your prediction should not be above 1 or below 0. And in probabilistic supervised machine learning, guaranteeing that is really quite straightforward just by making sure that the distribution you pick, so there's always going to be some probability distribution associated with the output. Make sure that the probability distribution you pick actually has the right domain for the output variable. In this case, y is unconstrained, so I could have picked any one distribution that has an unconstrained support. So the support of a distribution is all the values that have a non-zero probability in that distribution. So I could have picked, again, like in this case, I picked a normal distribution, but any other distribution, like a t distribution or some other distribution that has like a Cauchy or something like that, although Cauchy is a bit special, so maybe we want to stay away from that most of the time. But yeah, so basically any distribution that has this minus infinity to plus infinity support would have been fine to use in this case. Good. And so in this case, we picked the normal distribution. The normal distribution has two parameters. One is the mean and the other is the covariance matrix. And so in this case, the prediction is actually usually the mean of the distribution. And so when I give you a new value x, for example, and I ask you what is the prediction for this new value x, usually the procedure is you evaluate the mean of the distribution of y conditional on x, which in this case is this f of x, like this function f. We'll talk about the function f. But this function f can be used to evaluate the mean of the distribution of y given x, and that's usually our prediction. Now, if we're trying to simulate from this model, we can, but then we'll need the full distribution. So we need not just the mean, but also the covariance matrix of y, which is often also fitted to the data. In more traditional linear regression, you mostly estimate the mean and you make some assumptions about the variance being constant, for example, and you only care really about the mean for the most part, and less so about the variance. But the variance comes into play when you're estimating confidence intervals and things like that. But in supervised linear regression, or at least the way that we recommend you think about this, is that there's always going to be a distribution associated with the output. In probabilistic supervised machine learning, I should emphasize, because non-probabilistic supervised machine learning will not assume a certain distribution, right? It will not try to make that assumption. But at least in the probabilistic version of it, we do have to make that assumption, and the assumption here in this particular model is that y is a Gaussian with mean f of x and covariance matrix sigma. Now, the value of f of x, or the function f itself, could be any arbitrary function. Right? It's a function that takes input x, but it could be a linear function, for example, with certain coefficients. It could be a nonlinear function or a neural network with certain parameters associated with it. And so the function f here is really an arbitrary function that can have parameters of its own. And the goal of supervised machine learning is to then learn the parameters of the function f, as well as learn the value of sigma. And sometimes sigma itself can be actually a function of x as well. Right? So there's no reason that sigma would not be allowed to be a function of x. In this case, sigma is sort of a constant, but it can also itself be a function of x, in which case the function should output a positive definite matrix, because sigma here, if we're assuming that y is multidimensional, and this is a multivariate normal distribution, then sigma here is a covariance matrix that has to be positive definite, essentially. And so the function that we define has to always output a positive definite matrix. Similarly here, the function here has to output a value that's the mean of a normal distribution. Now, the mean of a normal distribution is unconstrained, because the normal distribution itself is unconstrained, and its mean is also unconstrained. But the which means it can be, again, going all the way from minus infinity to plus infinity. And the output domain of the range, I suppose, or codomain of the function f here, the set of values that f can output should also be consistent with the set of values that this parameter can take. So in this particular case, the parameter is allowed to be, again, unconstrained from minus infinity to plus infinity. And so f should be able to output values from minus infinity to plus infinity for different values x. For different inputs x, all these different output values should be plausible. right? Obviously, minus infinity and plus infinity themselves are not included, but just everything else in between should be. Now, in the case of the sigma, I cannot output a sigma of minus 1, for example, or a 1 by 1 matrix that has just a value minus 1, because that's not a valid covariance matrix. And so if I define this as a parameter, then I have to make sure it's constrained to be a proper covariance matrix or a positive definite matrix so that it can actually be used and interpreted as a covariance matrix. Otherwise, it cannot be interpreted as a covariance matrix. Now, if I'm defining it as a function, I need to make sure that the function outputs such a matrix as well. So that's a very important consideration, is actually when you're using a specific distribution, you need to reason about and make sense of what does each parameter actually mean, what is the domain of that parameter, how to make sure that that domain is respected when you're defining a function to output this parameter. Because we're going to be doing this a lot, is defining a function that outputs a parameter of a distribution. So it's very important to keep that in mind. Now, what happens if our response is actually positive? In this case, basically, we can switch the distribution from being a normal distribution to being a log normal distribution. And the log normal distribution is basically similar to saying that the log of y is normally distributed. So when I say that y is log normally distributed, it's the same thing as saying that log of y is normally distributed, which means I could be sampling values from the normal distribution and then basically taking its exponential, because that's log of y, so take the exponential of that, and that gives me samples of y. So it's always good to think of what is the sampling process, what is the sampling procedure when I define a distribution, how do I sample from this distribution? And the way to sample from a log normal distribution is to first sample from the normal distribution, and then take the exponential. And actually the log normal distribution is usually parameterized not by f of x, but by log of it. So not by sort of the median of f of x, but by sort of the log of the median. So if f of x here was sort of the prediction for y, here this, and if we assume that f of x here is also the prediction for y, then technically this should have been log of f of x. But that's at least in the programming. When you're defining the distribution in Julia, you define it in terms of the log of the median and not the median itself. This here would be the median rather than the mean, but this is also both the mean and the median in the normal case. So it's important to keep that in mind, that depending on the implementation of a log normal distribution, sometimes you pass in maybe the median itself, sometimes you pass in the log of the median, and in any case, I think the function f here is sort of an arbitrary function, and actually in this case, the median is the elementwise exponential of f of x. So this f of x is not the same interpretation as this f of x. In this particular sort of slide, f of x here is in log scale, whereas f of x here is not in log scale. Right, so that's why we're able to use the same, or we're able to use f of x in both cases, but they actually mean different things. Right, and again, in Julia, when you're actually passing in the first parameter, it's usually the log scale or the log of the median, and not the median itself. Right, and then the exponential of that would be the actual median of the log normal distribution. But it is nevertheless still a function of x, and it's a function of x. And when you're working in log scale or the log of y, the output is still unconstrained. Right, so we can define a function here, an arbitrary function that has an unconstrained output, and that represents essentially the log of the median of that distribution. Now, sigma has the same interpretation as before. It's the covariance matrix of the underlying normal distribution. Right, so as we said, when we're sampling from this, we first sample from this normal distribution, which in log scale, you can think of this as sampling in log scale, sampling for y, but in log scale, where the mean of that distribution, which is also the median, is f of x, and the covariance matrix is sigma, and then once we have those samples, we simply undo the log just by taking the exponential, and then we get samples for y. Right? And so these are two examples of models that we could define that can be used for prediction. In this case, the prediction would be f of x, and in this case, the prediction would be the exponential of f of x, or the median, essentially, of the distribution. Now, you could also get the mean of the log normal distribution, but it's not one of the parameters. It's a derived quantity that you can calculate based on the parameters of the distribution. Good. Now let's talk about classification. So in classification, all we have to do is actually, if you think about it, just change the distribution of y here, because now we're going from a continuous value for y to a discrete values for y, right? And so previously y could be any value from minus infinity to plus infinity, or any value that's more than 0. But now y is basically just a set of discrete values. So if it's a binary classification problem, we can assume that the only two values that y can take is either 0 or 1, essentially. And the only distribution for such a random variable is actually known as a Bernoulli distribution. Now, intuitively, a Bernoulli distribution is just a coin flip distribution, which whenever you have only two choices, there's only one distribution you can define. There aren't that many choices. And that distribution is always parameterized by the probability of one of the outcomes. So usually it's the probability of getting 1 and not 0. And then that's basically the only parameter of that distribution. And because it's a probability, it has to be between 0 and 1, because it doesn't make sense for the probability to get, for example, one of the outcomes, or to get the outcome equals 1, that's more than 1, that is like 200%. That would not be interpreted as a probability. And so, because the only parameter for Bernoulli distribution is a probability itself, the way that we have to parameterize it is such that it's between 0 and 1. And the way we are doing this here is by defining our same old function f. So this function f here outputs values that are between minus infinity and plus infinity. It's unconstrained. And then the way we take that and then constrain it is by passing it to a function that essentially only has output between 0 and 1. So this function here is the logistic function, which looks like this. It only takes values between 0 and 1. And so when the input, so in this case the input is called z, which would be f of x essentially, all of this would be passed in here as z. When z takes value minus infinity, this here actually takes a value of 0. Right, because when z is minus infinity, the exponential of infinity would be close to, like, obviously infinity as well, and so 1 over infinity is 0. Now, actually, we don't actually divide by infinity, but it's more of a limit argument that as z gets bigger and bigger, or rather smaller and smaller, or a larger negative number, this gets this becomes a large positive number, and then this whole ratio becomes close to 0. And so as f of x approaches minus infinity, logistic of f of x approaches 0. And as f of x approaches plus infinity, then logistic of f of x approaches 1. So they never actually reach 0 and 1 in exact arithmetic. Of course, when you're approximating, sometimes it's like 10 to the power of minus 20. So that's close enough to 0, and the computer will just approximate that as 0. But they never actually, in theory, reach 0 or 1, essentially. But the domain, or the codomain, or the range, or the output domain of the logistic function is basically between 0 and 1. Right? Whereas the input that it accepts can be any kind of input from minus infinity to plus infinity, excluding the infinities. So that's a Bernoulli distribution, and that will define, again, the probability that y here takes a value of 0 or 1. Right? When we're sampling from this, we basically calculate this probability here, and then do a coin flip, and based on the coin flip, well, it's not really a coin flip, but let's say it's a computer-generated coin flip where the coin is biased to a certain degree so that it has one or a slightly higher probability, let's say, of getting one side than the other. And then we get a value for y to be either 0 or 1. So that's sort of the idea. Typically, you can sample a value between 0 and 1, and if it's less than or equal to the probability, then it becomes 1, and if it's more than that probability, then it's 0. So there are many sampling routines that can be used, but that's out of scope for this course. But again, intuitively, the idea here is that it's just a coin flip with biased coins, and the level of bias is determined by this probability here, which itself is parameterized by a function called f of x. The function f of x has its own parameters that we are supposed to fit. So we're supposed to learn those parameters from the data with a certain objective function value in mind, which we will talk about in a minute. Now, in the case when we have multiple classes, and this is here, it's often called multinomial classification. So think if you have, again, multiple categories, not just two categories, so not just cat and dog, but maybe cat, dog, and bird and lion or something like that. So you might have 4 different categories where you're trying to classify an image into one of these basically bins. So which of those bins does this image fall into? In that case, we can use a appropriately named distribution called the categorical distribution, and it's just a basically multinomial sort of equivalent or version of the Bernoulli distribution, where we don't just have 2 categories, but we have multiple categories. And so we often call these classes in machine learning or in supervised machine learning, coming from the word classification. So the class is just the category. Sometimes it's called a group as well in pharmacometrics. But let's just call them, let's say, classes or categories. The distribution name is categorical, and the way that this distribution is parametrized is very similar to the way the Bernoulli distribution is parametrized. It's just that now we don't just have a single parameter. We actually have, let's say if we have k classes here, then usually we have k minus 1 parameters, essentially. And the way it's actually written out is it's written out like this, where we define something called a softmax function. And the softmax function, so that's a very common way to parameterize it, but there might be other ways to parameterize it as well. But the softmax function essentially takes in a vector of length k, although there's perhaps one additional, like k minus 1 should have been sufficient, but let's assume that f of x now returns a vector of length k, and those values can be from minus infinity to plus infinity. So now f here is actually vector valued, and you notice this from the bold syntax here compared to the regular font here. And so f here actually returns a vector, essentially, and it's a vector of length k. So if I have k equals 2 or k equals 3, then this would be a vector of length 3. And its values from minus infinity to plus infinity. Now, the softmax function, which takes this form here, what it does is it takes these values that are unconstrained, essentially, from minus infinity to plus infinity, and it returns a vector such that all the values in that vector are between 0 and 1, and such that the sum of all these values is equal to 1. Right? So I repeat, all the values in that vector are between 0 and 1, but the sum of these values is equal to 1. And basically what that means is we can now interpret, these are all valid probabilities for the different categories. And so the first probability, for example, would be e to the first input divided by, or the exponential of the first input divided by the sum of the exponentials of all the inputs. And the second would be, again, the exponential of the second input divided by the sum of the exponentials of all the inputs, and so on. And so these numbers here, these outputs, are now interpretable or can be used as probabilities in the categorical distribution. And again, you can actually reparameterize this a bit such that you only need actually k minus 1 rather than k inputs, because really you only have k minus 1 degrees of freedom and not actually k degrees of freedom here, because the sum of all the probabilities has to be equal to 1. So once you've defined the first k minus 1 probabilities, the last probability is always 1 minus the sum of the previous ones, and there is no additional room to define that any other way, essentially. Now, in both of these cases, regardless of how we parameterize it, in both of these cases, usually the prediction is the mode of the distribution. So we've seen cases where the prediction might be the mean, like in the normal distribution, or the mode, or the median, because all three statistics are basically the same for a normal distribution. And we've seen cases where it might make more sense to use the median as a prediction here, although you can also compute the mean, but the median falls more naturally out of the parameterization of a log normal distribution. And then there are cases where the prediction can also be the mode of the distribution, which is often in the categorical case, especially if it's multi-node, like if it's a nominal data where there is no order, like the order doesn't really matter between the data. Then in this case, actually, you we can't take the average of a cat and a dog and say, well, it's half 50% cat, 50% dog. That's not very useful as a prediction, but usually what happens is you take the value that has the highest probability, and so if this here is more than 0.5, then you predict 1, whatever 1 actually indicates. Could be that 1 indicates a dog and 0 indicates a cat. And so if this here is more than 0.5, you predict 1. If this is less than 0.5, you predict 0. If it's exactly 0.5, then you can just round it up and predict 1 as well. Now, same thing with the categorical distribution here. You take a look at all the probabilities that you get, the vector of probabilities here, one probability for each class, and then you predict the one that has the highest probability. So if the third class has the highest probability, then that's your prediction, essentially. And that's actually the mode of that distribution. Now, if you have a tie, then you can just do an arbitrary tiebreaker. Just take the first one, for example, from the group. and that should be sufficient. Now, you can probably immediately see that this mode prediction here doesn't necessarily capture the full uncertainty, and that maybe there's actually value in capturing the full uncertainty, and that's true. And so if you're trying to simulate, for example, instead of just predicting, you would be simulating. Let's say if there is a 60% chance that it's a dog and 60% chance that it's a cat, you'd be simulating 60% of the time a dog and 40% of the time a cat, right? Or if it's a probability 60% that it's a responder and 40% that it's a non-responder, then you would be simulating 60% of the time that this patient with this particular characteristics X here is a responder, and 40% of the time that it's a non-responder, right? And so when you're simulating, you're actually simulating directly from that distribution. Now, whether it's well calibrated or not, and whether it fits the data or not, that's a separate question. But at least if you don't want a single prediction, then you probably want some form of simulation to be performed instead. Good. So that hardly scratches the surface of probabilistic supervised machine learning, but it sort of gives you some idea about how we approach these problems, and especially in the context of a modeling environment like Pumas or DeepPumas, these sort of modeling choices of which distribution, how to parameterize it, that's really the main decisions, or those are the main decisions you have to make as a modeler, and the details of how to fit them and what's the objective function and all that. Of course, they're very useful and very important, but often they're hidden away from you as a user. And so, at least in terms of the theory needed to be able to use these tools, this pretty much covers quite a bit of it, despite being, again, barely scratching the surface of what can actually be done and on all the math and the theory. But maybe let's continue our quick tour through some of these concepts and move on to probabilistic unsupervised machine learning. Next. So with unsupervised machine learning, we usually have what's called unlabeled data. Now, unlabeled data, previously we had X and Y, where X was the input and Y was the output or the label. Now, let's just call everything Y. Now, you'll find people sometimes just calling everything X. In this case, we'll just call everything Y because, again, like usually Y is the variable we actually care about in supervised. In unsupervised, we care about all of the data, essentially, and learning something from the data. So we're just labeling the whole thing as Y. And we have instances of this data Y here. So we could just have some, for example, data about the covariates. So think of Y here as a bunch of covariates or a bunch of biomarker data or a bunch of tumor size data or survival data. So any kind of data that's, again, I care about modeling the entire data or doing something with the entire data and not just answering a conditional question, which is what is Y given X, right? So I'm not just interested in Y given something else. I'm actually interested in Y itself and sort of the marginal distribution of Y in that case. And you can think of just like X and Y now being merged together, and you just concatenate them in one big vector, and now it's just one object basically that you need to work with. Let's say the joint distribution of X and Y in that case. Now, what are the possible tasks, or what are some of the common tasks in unsupervised machine learning? One very common task is learning the data distribution. So I have this data Y, and one goal that you might have in mind is, okay, I would like to learn a distribution such that it captures the essence of this data Y. So let's say I give you 1 million data points. That's a luxury in our field. Usually we don't have 1 million data points. But let's say I give you 1 million data points. Maybe those 1 million data points actually come from a normal distribution, in which case you don't need to keep the 1 million data points on you at all times to be able to do anything useful. Maybe if we just fit a normal distribution to this data, we can actually get the mean and the variance, for example, and then those two, they're often called summary statistics or sufficient statistics in this case. Those two sufficient statistics are sufficient and they represent all the information, they hold all the information that you have in your data. And so I can now get rid of my 1 million data points, right, and save my memory and only keep two values, basically the mean and the variance, that represent the parameters of a distribution from which this data was most likely generated. And the benefit of this is there are multiple benefits. First, it tells me something about the structure of the data. Right? It tells me that this data was sampled from a normal distribution with a specific mean and a specific variance. Now that might be useful information. Second, I don't need to keep the full data around if I'm trying to simulate, for example, or make some decision. I can always simulate from this distribution and generate, so use it as a generative model. Essentially, and generate new values y without ever having to keep or store the original y values, right? So learning the data distribution is a very valuable task that can be used for sort of to answer multiple different questions, and therefore it is one of the standard tasks of unsupervised machine learning. Is what is the distribution of y? Now, if y here is a very like high dimensional data, for example, biomarker data or an image or something like that, often the distribution is not just a simple normal distribution, right? And that brings us to the whole field of generative modeling, of which large language models would be considered a subclass of these models here. So generative models is basically just another fancy name for a distribution or a model that can be used to sample data that looks like the real data or generate data that looks like the real data. And so there are many different generative models that basically, if you think about it, they just generalize the concept of just this normal distribution or fitting a distribution to the data, using perhaps some fancier models and different that have different graphical and causal structures or associative structures between the different variables. So we'll come to more generative models later, but again, in essence, the idea here is that we're trying to define a distribution or a family of distributions such that we can fit this distribution or the parameters of this distribution to the values of the data that we have, the observed data that we have, and then learn or basically have this learned distribution around and then use it to answer certain questions. Now, a second task that's quite common in unsupervised machine learning is dimension reduction. And related to that is often you'd see the term feature extraction or embedding. Embedding is a relatively more recent sort of buzzword with a lot of the generative modeling literature. They like to use that term, embedding, but it basically refers to the idea that given if yi here is high dimensional, so let's say it's an image with thousands of pixels, then I don't need to keep or like all these different pixels, all these thousands of pixels don't carry any meaningful information. Or let's say there's like 10,000 pixels. I don't have 10,000 bits of meaningful information in this image. Perhaps the image just encodes whether that animal is a cat or a dog, or maybe that's all I care about, right? Or perhaps like the most important parts of the image can be represented using only 3 or 4 values. So maybe what's the background color, what's the context of the image, what's the main character of the image, or something like that. And so the actual amount of information can be much, much lower dimensional than the actual dimension of the data. Now, in the context of pharmacometrics, if I have 100 biomarkers, for example, extracted from, let's say, brain signals, then the different positions of the sensors on the brain or on the head don't necessarily give you different information, right? Again, just like images, there's this spatial correlation where 2 sensors next to each other, they most likely give you some information that might be correlated with each other, right? And so they don't actually have completely new information or bring completely new information to the table. And so even 100 biomarker signals could actually be just like the actual dimensionality of information in that could be 2 or 3 or 4 dimensional, right? Or maybe 10 dimensional, but not 100. And so the question is, how do we extract these meaningful features or meaningful values that are basically interpreted, or you can think of it as a function of your data, but it's a lower dimensional function. So my data is high dimensional, but I would like only 3, 4, 5 values that capture the essence of this data, that capture the information content of this data. And that's an abstract concept, but we'll come to more specific examples of what that means. But that concept is often called dimension reduction. And a very common dimension reduction method that many of you might be familiar with is principal component analysis. Now, if you think about it, principal component analysis reduces essentially, let's say I have 10 dimensions or 20 dimensions. It tries to find the directions along which there is maximum variance. And then it ignores all the other dimensions, essentially. And so you can project then your data point, let's say your 100-dimensional data point, onto just maybe 3 values. Those 3 values are the projections along the principal components with the maximum variance. And the hope is that then, because this has the most variance, or these dimensions have the most variance, that they explain the most important and significant bits of information about your data, right? The idea here is that low variance components or low variance directions are most likely going to be less informative than high variance directions, right? That's a bit of a hypothesis, but that's sort of the idea behind this. And so so dimension reduction, again, is all about learning these lower dimensional representations, and the term representation will come out a lot in this concept, or in this whole field of unsupervised machine learning, but it's about learning this lower dimensional representation of your high dimensional data. Right? Now, you can think of this lower dimensional representation as a feature. So if I'm looking at an image, I'm extracting certain features, like I could do manual feature extraction, where a human actually sits down and looks at the image and be like, okay, the background here is green, the background is grass, the animal is a dog, the activity that the dog is running on the grass. Right? So I could actually do this feature extraction manually, but you can think of unsupervised machine learning, or this specific task in unsupervised machine learning, as a way to extract features automatically from the data. Right? Now, those features may not mean anything per se. They may not, when I say they may not mean anything, is that each one of those features may not correspond to a very clear concept that we have. They may not be interpretable, for example, unless you explicitly design them to be, and there are ways to do that. But the first value, for example, in PCA may not correspond to the color of the image. Right? If I do PCA on the pixels, for example, the first value in the projection on the principal components does not correspond to a specific concept that I can point my finger to and be like, this is what this value actually measures. So that's not usually the case. Usually all these sort of concepts are entangled together in these values, and there's no easy way to tell them apart, except, again, if you design your dimension reduction or your representation learning algorithm to actually encode certain concepts in the lower dimensional vector. And so, but more generally, again, you can think of this still as essentially automatic feature extraction. Now, another word for this feature vector that you get at the end is embedding. So if you ever hear the word embedding mentioned in the context of generative models, it just refers to this idea of a lower dimensional. Usually it's a lower dimensional. It doesn't quite have to be, but it's some fixed length representation of your data, essentially. That, again, usually is lower dimensional, but strictly it doesn't have to be. And that's often called embedding. Good. Now, another task that's quite common, and it falls under the umbrella of unsupervised machine learning, is clustering. Now, what is clustering? Clustering is when I give you some data points and you would like to divide this data between, let's say, 2 or 3 or 4 groups. So let's say in the simple case is I give you some tumor size data over time. And I ask you to tell me how many different subgroups exist in this data set. That activity, that task, is commonly known as clustering, and the group that we, or based on like how we divide them together, or how divide these points in different groups, each group would be called a cluster, essentially a cluster of points. And so clustering / grouping is essentially another task in unsupervised learning, and again, you can think of it as just extracting features again from the data, but the feature is more discrete, essentially, where I'm saying that these 10 data points belong to this one group and these other 10 points belong to this other group. And so another way to say this is that the first 10 points have a feature of 0 and the second 10 points have a feature of 1. Right, so it's like I'm extracting features from the data, but the feature is discrete. Right, it's either 0, 1, 2, 3, etc. Where the number here is arbitrary. You can assign it and stick to it, but the number actually doesn't mean anything. It just means a separate group, essentially. Good. So that's the task these are common tasks in unsupervised machine learning. But then there are many different ways to go about doing these, and some are probabilistic in nature, and some are non-probabilistic in nature. In this sort of section, we focus mostly on probabilistic methods for doing unsupervised machine learning. And in most of these methods, essentially, the goal is almost always to learn a generative model. And so despite these seeming like different tasks, you can actually do them all using the same model structure. And so once I define a generative model, So basically dimension reduction, feature extraction, embedding, generation, clustering, these can all be done once you've actually done this. So in essence, this is sort of almost the main task that we can focus on. And once we do this using a probabilistic model, there tends to be quite straightforward ways to actually do the other tasks as well. But this is sort of the most difficult task that we can focus on. And so usually the goal when we're defining a probabilistic model for unsupervised learning is to define a so-called generative model, which again is just a fancy name for a simulation model or even just a simple distribution. Right? You can think of it as a distribution that just is more complicated than any of the common distributions that you may know about from probability and statistics. And so the goal again is to define this generative model. Now, how do we do this? Sort of in general, there's a general structure that is common in unsupervised machine learning. Of course, you can define any kind of model that you want, and for different domains, it may make sense to like draw the sort of graphical model or probabilistic graphical model for that domain that you are working in, and define all sort of the potential causal structure between your data points and potential correlations and so on. And so you can go about this in a like very detailed way that's very domain specific. In essence, most of the models that we build for PKPD and pharmacometrics, most of these models can be actually called generative models. And we'll come to that in towards the end of the slide deck here. But whenever you can simulate from a model, basically your model can be called technically a generative model. Good. So one common structure, this is not the only structure, but one common structure is to define something called a latent random variable and call it Z. In this case, it's the common notation for that latent variable. And this latent variable can be really taking any distribution that we want. The distribution can have parameters, or we can fix those parameters. In this case, we decided to fix them. And so Z here would have a mean value of 0 and a covariance matrix identity. So that's a very normal sort of, it's actually the normal distribution, standard Gaussian distribution, right? So it has mean 0, standard, the covariance matrix is the identity matrix. Now, once we define this, we can also define a distribution or a model for y given z. So if I give you a value of z, then the model should describe how to go from z to then a distribution for y. Then we can sample from that distribution to get the actual values of y, right? So usually there are two components. First is the latent variable z, and then some conditional model or conditional distribution of y given z, right? Now, once we have these two components here, often or quite usually we can either approximately or exactly get the inverse distribution, right? So this is often called the inverse distribution or the posterior distribution. If you have more of a Bayesian background, the more common name would be the posterior distribution of what is z given y. So if I give you y instead of giving you z, if I tell you this is a real observation y now, this is a real image y, what is the value of z that may have generated this value of y, right? And maybe there are multiple such values, and that would be called the posterior distribution, or the distribution over these values is called the posterior distribution of z given y, right? But this is defined implicitly. This is not usually encoded explicitly, at least in most generative models it's not. In some generative models it is. But you can think of sort of the more common approach is that you're defining your latent variables, you're defining your conditional model here, and then we're able to actually either approximately or exactly infer the inverse of that from your model and your data directly. So that's the framework that we're going to be working in most of the time. So let's take some examples. So if we have a very simple case where z is a normal distribution and then y is also a normal distribution, but the mean of y is a times z, where a is a parameter, it's a matrix in this case, plus b. So we have a linear regression model basically built into that, or a linear model, or an affine model. So usually the difference between linear and affine is that linear actually technically only refers to this part here, a times z. Affine, when I say an affine function, it's a linear plus a constant, or plus an intercept. That's the more sort of rigorous definition of linear versus affine, but usually people refer to this whole thing as a linear regression model and just call it a day. But yeah, so this is a linear model here, or an affine model, if you want to call it. And this is the mean, or it describes the conditional mean of y given z, right? So to evaluate this, I actually need a value for z. Like let's say I managed to substitute values for A and substitute values for B. So these are parameters. I can just plug them in. Usually you would fit them to the data, or you figure out what the best parameter values are given your data. But let's assume that A here is fixed and B is fixed and sigma is fixed. Okay, so these are all just standard parameters. We fix them to some values. Now, in order to evaluate the mean for Y, I actually still need a value for Z. And that value for Z is defined according to this normal distribution. So if you think of this as a generative model, how would you actually generate data from this? Is by first simulating values for Z from the normal distribution, and then plugging in the value for Z here. We already have A, we have B. These are assumed to be constants here. Then we can calculate the mean of the distribution of Y given Z. So that's the conditional distribution of Y given Z. And then we have the covariance matrix, so that fully defines our normal distribution for Y. Then we can sample values for Y from that distribution. And so this here actually fully defines a generative model for Y given Z. Now, once we have that, I did say that we can approximately or exactly infer the inverse distribution. In this particular case, actually, the inverse of Z given Y. So if I give you Y now, instead of giving you Z, if I give you a real observation Y, the probability of all the likely values Z that may have generated Y, I can actually write this in closed form. So this has a closed form expression for the so-called posterior distribution of Z given Y. But that's not the main focus here. The main focus is that we are trying to build a generative model, or sometimes it's called a data generating process. So we're like writing out the process for generating our data. And this doesn't necessarily have to be the real process for generating the data, but it's sort of just a mathematical construct that we define such that we can learn the distribution of our data. You can think of this as a family of distributions, essentially, because I can simulate from it, I can sample from it. You can think of this as a distribution. And the distribution now is not just parameterized by a simple mean and variance, or by just 2 or 3 parameters. It could be parameterized by A, B, and sigma, right? So I can have arbitrarily complex functions here, for example. It wouldn't be called a probabilistic principal component analysis. It wouldn't be just a simple linear model, but I can have arbitrarily complex functions, and that would be, and those would have many parameters, like thousands of parameters. And in essence, what you can think of this is as a distribution with just many parameters, right? So I just managed to define my own now fancy distribution that has a lot more parameters than just a simple normal distribution. All right, now it can still be built based on normal distributions. I can have a normal distribution latent variable, some fancy nonlinear function here, and then a normal distribution here, and then I can stack another function on top of it, another distribution on top of it. So I can build my fancy distribution using building blocks. Each of them might be a normal distribution and some either linear or nonlinear functions, but then the overall distribution of Y would no longer be, most of the time, a normal distribution. In this particular case, actually, the overall distribution of Y is still a normal distribution. But if I have a nonlinearity here, then I break the normality, essentially. What I'm trying to get to is that this is just a fancy way to define your own distribution that has more parameters, essentially. That's what a generative model is. Now, this particular model is called a probabilistic principal component analysis model, and the idea is that it is similar to PCA or standard PCA, but it does sort of do the same job as a PCA, or similar, not quite exactly the same, using probabilistic modeling. And the goal here is that Z would be a lower dimensional vector than Y. So if Z here is only like 2 dimensions and Y is like 10 dimensional, essentially, then that's similar to doing PCA and only having 2 principal components at the end. Or at least when you get the inverse of Z given Y, it would be similar to that. And so this is part of a probabilistic principal component analysis, because in probabilistic PCA, the goal is usually actually the inverse distribution is what we're interested in. But that's just the derived distribution. You can actually write it in closed form given this sort of data generating process that we define. Right? So given the forward process for simulating, we can easily derive the inverse distribution from that. And as we'll see later as well, there's more derivations later about this, but this is essentially equivalent to a linear mixed effects model. If you come from the mixed effects modeling world, this would be quite similar to a linear mixed effects model, and more detailed equivalence will be shown later. At least without covariance so far. And I think another name for this, also from the statistics world, is factor analysis. Although these models often vary slightly in the way they define sigma, whether it's a diagonal matrix or non-diagonal matrix, or just a simple scalar times identity. So the way that sigma is defined is often slightly different in these classes of models. Good. Now, another very similar kind of model structure is called a variational autoencoder. And again, we're only focused on the data generating part of that process, not on the inverse part. And the inverse part, we'll come to that again towards the end of the slides, but just focusing on the data generating part, or the simulation sort of component of the model. It's basically very similar to a probabilistic principal component analysis, where the only difference is we actually make use of neural networks. And we'll see what a neural network is a bit later, and what it's made of. But you can think of a neural network just more as a fancy nonlinear function with a lot of parameters. So I can define this very flexible function with maybe thousands of parameters, and it takes some input because it's a function, gives an output because it's a function, and I can then sort of constrain the output in different ways, or I can even constrain the input. Usually that's not necessary, but you can if you want to, in different ways. And then you just define the function and use it just like a normal mathematical function. So in this case here, I am replacing this linear function essentially with a nonlinear function, which is just a neural network. Now again, this could be arbitrarily complex, or could be quite simple. That's left up to you, the modeler, to decide what is actually required. Perhaps a data set is quite simple. It doesn't need a lot of nonlinearity in the distribution, but then if a data is more complicated, then it often needs some nonlinearity here to be added, or more rich or more flexible function or neural network to be used in this model here. Now, the first function here, so here I have two neural networks. One neural network actually gives out, the output of that neural network would be the mean. So the output of that neural network, let's say y here is 10 dimensional, the output here would be a vector of length 10. Right? It's just the mean of the distribution of y. So when can y be 10 dimensional? If it describes, for example, 10 biomarkers at the same time. Right, then it could potentially be, or 10 biomarkers at specific points in time. Let's fix the time for now for simplicity. Or if y here is a vector of length 10, that's again 10 covariates, for example, so 10 characteristics of a patient. Y could be a very low resolution image, that's only a 10 dimensional image. Of course, it can be more than 10. But sort of the idea here is that y represents a specific object or a specific data point that we can define, right? It could be biomarkers, it could be images, it could be covariates, it could be anything that we want it to be, right? And so the output of n in here, or this first neural network, is essentially the same length as the vector y. Now, the second neural network here is this n sigma, and this one is supposed to essentially encode or give us as an output the covariance matrix of that normal distribution. Now, that might not be very obvious how we can actually do that, because the covariance matrix has to be a positive definite matrix, and in general the neural network will not output a positive definite matrix. So if this has to be, let's say, a 3x3 matrix, then the neural network can be made to output perhaps maybe just 6 different values from minus infinity to plus infinity, but then it cannot easily be made to give us a positive definite matrix. But actually there is an easy transformation that you can apply on top of that then makes that output a positive definite matrix. And so just like, for example, if you take the exponential of an unconstrained variable, it becomes positive or non-negative. You can do a similar kind of transformation. It's a bit more complicated, but it's possible to do, such that the output of an arbitrary function, if it has the right dimensionality, can be actually transformed and parametrized into essentially a positive definite matrix. And so this is just, again, a neural network that outputs a positive definite matrix that then has the interpretation of being the covariance matrix here. And a very simple structure of this is, if y here is high dimensional, you can think of this as, okay, like maybe we just want this to be a diagonal matrix, we don't want this to be anything fancy, or you can impose different kinds of structures on this, but usually a diagonal matrix is quite common here, in which case it's pretty easy to see how we can actually parameterize this as a positive definite matrix, because with a diagonal matrix, to make it positive definite, all you really have to do is make sure that the elements on the diagonal are all positive, right? So if we just define some neural network that outputs all the diagonal elements, and they're unconstrained initially, they can be negative, they can be positive. By taking the exponential of those diagonal elements, then we make them all positive or non-negative, or strictly positive in exact arithmetic. Then in that case, basically, this is a valid covariance matrix, right? It's just a diagonal covariance matrix. So it's quite straightforward to do this usually. But the main key point here is that these are both parameterized by the input z, and Z itself is generated from this distribution here, which is a standard distribution. That's sort of the main structure that we're going to be working with in a lot of these models. Now, taking another example, here is a GAN, or a generative adversarial network. So the way that, or the main difference between a GAN and a VAE or some other kind of generative models like the variation autoencoder here, in the generator part usually, the main difference is that we don't actually have additional noise on top, right? And this actually makes it quite difficult to train in general, because the way that we train or fit these models is using something called the marginal likelihood. But then when we don't have this sort of distribution at the top level, it makes it a bit more difficult to actually define, or a lot more difficult to define, what the marginal likelihood should be. And in that case, actually, the way this is trained is using some concept called adversarial learning, which we will cover in more details later, perhaps, or maybe in another course. And again, but the main sort of structure in the generator is that we don't have this layer of noise on top. You can think of all the randomness is encoded here directly in the latent variables and not adding it on top. And so in essence, the neural network just spits out the value of y directly rather than a distribution for y. Now, the other major difference between a GAN and a VAE is actually the way that they are trained, and not just this small architectural difference here. Because technically you can actually put a noise on top of the GAN as well. It's just because it's equivalent to having the epsilons or the noise terms being all part of this, for example. And so that sort of small architectural difference is not really the main characteristic difference between a GAN and a VAE, but rather it's the way they're trained as a result. But one way to sort of make sense of why GANs tend to work pretty well is that in some domains, for example, like imaging, we don't really have a good enough evidence to support that the overall distribution should be Gaussian. So if you think about it here, what that's really doing is just adding noise to the pixels. And so if I have a perfectly fine image and I add some noise to it, it becomes a blurry image, right? And so whenever I don't actually know what the true distribution of y given z should be, then maybe assuming that it's Gaussian may not always be ideal in all applications, because it might actually make it difficult to generate non-blurry images in that case, which would be problematic. And so again, is known for its ability to generate more crisp and sharp images, in part because it's not actually using this noise on top. But again, that makes it a bit more difficult to train, and that's where the whole adversarial part of the GAN comes in. And there is a technique called adversarial learning that's often used there. But fundamentally, as a generative model, it has a very similar structure to the previous generative models. Now, another quite popular generative model is called a Gaussian mixture model. Now, you may be familiar with this from other domains or from pharmacometrics, for example, but you can think of a Gaussian mixture model as essentially a special version of a generative model where the latent variable is actually discrete. And so if I have, let's say, 3 possible Gaussians or 3 subgroups in my Gaussian mixture, then I can define a categorical distribution here that takes some parameter vector. So this parameter vector is just the probability of each class in the prior. And you can think of this as a parameter that we can also tune and tweak and fit the data. So this could be a vector of parameters here, but they have to be constrained such that they're probabilities. So they have to be between 0 and 1, and their sum has to be equal to 1. Right? But it's just a vector of parameters. And this here is a categorical distribution that defines the distribution of the latent variable z, and z is essentially just the value between, let's say, 1, 2, 3. If I have 3 groups, then it could either be 1, 2, or 3. Right? It can be anything between them. And then depending on the value of z, I can use it as an index to actually use a different mean mu and a different sigma, or covariance matrix sigma here. And so for every group, I can have a different normal distribution, essentially. And so depending on the value of z that I get, I can use the first mean and the first sigma, or first mu and first sigma, or if z is equal to 2, I can use a second mu and second sigma. If z equals 3, I just use a third mu and third sigma. So I have 3 pairs of mu and sigma, essentially. And I have my latent variable z, which determines which of the normal distributions I should be sampling y from. Right? And so again, conceptually, it's just a generative model with a discrete latent variable. and an additional parameter vector here. So we're not just using sort of constants for the prior of Z. This is commonly known as the prior distribution as well of the latent variable. So I'm not just using constants here to parameterize it, but I'm using a vector of parameters that I also want to learn from the data. Now, you can think of this as essentially like maybe as we saw before, we can get, for example, in the probabilistic principal component analysis, if I get the inverse probability, which is the probability of Z given Y, and if Z has a lower dimensional than Y, then I can use this for dimension reduction, right, or feature extraction. So if I have Y here is 1000 dimensional and Z is only 3 dimensional, then by getting the distribution of Z given Y, and let's say taking the mean of that distribution, right, or any summary statistic of that distribution, that represents basically a feature extracted or some lower dimensional representation of Y, right? So for every Y, I'm asking what are the possible values of Z that could have generated this Y, and those values give me some lower dimensional representation, or let's say the mean of those values give me a lower dimensional representation of Y in this case. And same thing, I can do the inverse process here as well, or the inverse problem here. So given Y, what are the values of Z that may have generated this Y given this data generating process? Right? And there may not be a single unique value. There might be multiple different values, because in general these models are not going to be identifiable if they're nonlinear and like uses neural networks. And so there may be multiple such values of Z, that all of which could have generated Y. But then the distribution of those values is something that we can try to either approximate or sample from using, for example, Markov chain Monte Carlo or MCMC. And so there are techniques to basically try and approximate or sample from the inverse distribution or the posterior distribution of Z given Y. Now, in a very similar fashion, we can actually, in again, it's a little bit less straightforward how you can go from Y to Z, because we don't have a proper likelihood here. But there are ways to basically get the embedding of Z given Y. That also uses the concept of adversarial learning there. Now, in a Gaussian mixture model, you can think of the posterior probability of Z given Y as basically the probability of each group. So if I give you a data point Y, a new patient walks in through the door, they have their tumor size data, and then I give you that data, and then I ask you what is the probability that this patient is a responder versus a non-responder, or a complete responder versus a partial responder. Then you can assign different probabilities to each of those groups or each of those clusters. So that's basically a clustering task or a clustering exercise that we're doing. And then based on that posterior probability or posterior distribution of Z given Y, I can find what is the value of Z. Is it Z equals 1 or 2 or 3 that has the highest probability according to that posterior? So let's say it's 0.1 for Z equals 1, 0.2 for Z equals 2, and 0.7 for Z equals 3. Then with 70% probability, we are saying that Z is most likely going to be 3. Or Z is equal to 3 with 70% certainty, basically, according to the posterior distribution. Now, what that means is if I have to actually tell you, okay, what is the cluster, what is the group of Y, of this data point Y, I would most likely be picking Z equals 3. Right? Now, ideally, I don't want to pick just one and commit to just one. And ideally, I want to actually use the full posterior if possible, because that represents the true nature of your uncertainty about the value of the actual value of Z that Y sort of belongs to, or that could have generated Y. And it could be that Y can come from either 1, 2, or 3 with different probabilities. That's often the case. But if you have to really pick one, you would pick the mode of that distribution, which is the value of Z that has the highest probability. Right, and that's again obtained from this inverse distribution of Z given Y. In this case, because Z is a categorical or a discrete variable, both the prior is categorical and the posterior is also categorical. Right, so the prior distribution is just a categorical distribution with one probability assigned to each class or each group or each cluster, and then the posterior is also a categorical distribution, but with different probabilities associated with each cluster compared to the prior. And then we can pick, again, based on the posterior, what the actual most likely value is for that discrete latent variable given your data point. And that value is basically the cluster in a clustering task. right? So that's sort of you start to connect the dots a bit that, yeah, with many of these generative models, we're able to actually solve the inverse problem or approximate the inverse problem such that we're able to do either dimension reduction or some feature extraction or some clustering of some sort. And we'll see more details of that a bit later as well, and how it applies to or connects to nonlinear mixed effects modeling and what we commonly do in Pumas and DeepPumas, because they have a very sort of deep connection that we will explore. And that concludes the first part of this presentation. There will be more components or more parts of the slide deck coming up in the next few videos. But thanks for your attention.